Okay, and next up, let's see, I'd like to introduce Tom Mueller. Tom is president of Mueller Additive Manufacturing Solutions, and he's going to be talking to us about whether an Ultimaker 3D printing solution is viable for investment casting applications. So Tom, you want to go ahead and turn on your camera and audio for us? Take it away.
And I hope everybody can see this. Okay, I'll try and make this pretty quick. Basically, I'm going to talk about investment casting. And if you're not familiar with investment casting, it is a metal casting process. It's also known as lost wax casting, and it's used to make a lot of complex components. For example, most of the components in a jet engine are investment cast. Same for gas turbines. It's used to make medical implants like artificial hips and knees. It's also used to make a lot of sculpture. It starts with a wax pattern, and I'm not going to go into detail now, but basically the wax pattern is a copy of the metal part you want, and it's through the process is converted to metal. The drawback of the process is that it requires relatively expensive tooling to make those patterns. They're molded in a separate mold, much like an injection mold. That makes prototyping very expensive because of the cost of tooling. Now, a long time ago, additive manufacturing came to the rescue there by we developed a process to print patterns and use printed patterns instead of wax patterns for prototype castings. That was more than 25 years ago now, and it has become the standard way to prototype investment castings. It's used by 100% of the investment foundries in North America, and probably by about 96% of investment foundries worldwide. It has been one of the most successful additive manufacturing applications. It's not really recognizable because we're not making an end-use product, but we're making an intermediate step in the manufacturing process. Most of the patterns today are created by one of four printing technologies. The first is stereolithography. This uses a build style called quick cast, and the Pro X800 by 3D Systems is the most common system used to print those. Laser sintering is another process. They print polystyrene beads in a process material called cast form, and the S Pro 60 is probably the most common laser sintering machine used for that. Multi-jet modeling, particularly printing wax using an inkjet printing process, has become pretty popular, especially for smaller parts. The ProJet 3600 is one of the most common printers used for that. And then finally, binder jetting process via the VX1000 printer from VoxelJet using a polymethyl methacrylate powder is the most recent entrant there, and it has become pretty popular. Between these four technologies, they account for more than 98% of all the printed patterns that are cast in North America. I did an in-depth study of these systems a few years ago, and I'll be referring to some of that data from that study a little bit later on. I started hearing about a new technology being used for investment casting patterns a few years ago when I was visiting some foundries in China. And they were telling me about that they were experimenting with inexpensive material extrusion printers to print patterns. These were not home printers, the low-end industrial printers. If you're not familiar with the term extrusion, material extrusion printers, it's also known as FDM printers, fused deposition manufacturing. This is the way they work, and of course, this is the technology that Ultimaker uses. There are now several models and manufacturers of this, but I wondered, are these really viable for pattern printing? And to be honest, I was convinced they were not. They were not serious printers for industry, that they were good for a home market, but not necessarily for the kinds of applications that I was looking at in investment casting. Well, about a year ago, Greg asked me to help evaluate their S5 printer for investment casting. So I took on the project. We used an S5. We use the polycast filament. This is not an Ultimaker material, but it's one that was developed specifically for investment casting. I worked with a local foundry here, Wisconsin Precision Casting, and we tried to evaluate its use for investment casting applications. Now and this is the S5 printer. To make a printed pattern, we want to use a hollow build style for a number of reasons. First, it minimizes the amount of material we're going to use in the pattern. Secondly, it increases the print speed. And finally, it reduces failures in the casting process due to thermal expansion. And I won't go into detail here, but there will be a longer version of this. I'm not sure exactly when it's going to be yet, but I'll go into more detail there. There are a variety of infill settings available through the Cura program, like these. Wisconsin Precision did some testing and selected a 10% triangular infill and a 0.2 millimeter skin thickness, and that was what was used for the evaluation. Now, how do we evaluate this? I looked at a number of criteria that foundries would be concerned about. The first is build envelope. How big a part can you build? If the average size of castings they make is 12 inches, but you can only build a 4-inch part, the printer won't be much use to them. So they want to know how big a part they can build. Second is accuracy. The casting that they're going to create can be no more accurate than the pattern they start with. So accuracy becomes a very important consideration. Surface roughness. Like accuracy, the casting they can create can be no smoother than the pattern they start with. So surface roughness is an important consideration. Print speed. If it takes a week to print a pattern, it's not going to be of much use to anybody. So they're very concerned about how fast they can print patterns. Printer cost. Most of the foundries are low to medium sales volume businesses. They really can't afford to spend $1 million for a printer, so they're very concerned about how much that printer is going to cost. And just as important is pattern cost. How much does it cost to make a pattern once they've got the printer in-house? The final consideration is casting difficulty. All of these processes, except for the printed wax, require a different casting process than they use for the molded wax patterns they work with every day. The more deviation there is from that process, the more difficult it is and the more expensive it is for them to cast printed patterns. So we're going to look at each one of these. Now, these first 4 are measures of printer performance. The next 2 are measures of operating cost. And the last one is a measure of casting performance, and that's primarily due to the pattern material that we're using, in this case, the polycast. So looking first at build envelope. This, of course, is the size of the maximum part you can build in a printer. With the Ultimaker S5, it's 330 by 240 by 300 millimeters. Wisconsin Precision estimated this would accommodate 50 to 70% of the parts they cast. So it took a good chunk of their business. How does this compare to other ones? And here I'm using the data from my study previously. It's not anywhere close to the larger machines like the VX1000 or the Pro X800, but it's actually larger than the ProJet 3600 by more than a factor of 2. Accuracy. Accuracy information is really difficult to find. It varies a lot with a bunch of build parameters like build orientation and the layer thickness. But we wanted to get a little bit more quantitative data. So we used this test artifact, was one we developed. It's basically 9 stacked cubes. There's a hole in each face of each cube, and there's 3 flat faces on this part. Each one looks like this. There's 6 linear dimensions, which are outside dimensions, 6 diameters, which are inside dimensions. So between the 3 faces, we get 36 dimensions per part. The measurements of the Ultimaker and some of the competing technologies were done at the University of Northern Iowa. What we did was calculate the dimensional error for each one of these 36 dimensions and then average the absolute value of that error. And I was surprised. This is the way it came out. Ultimaker gave us the most accurate part. Now, this is a very small sample size, and I would not draw any serious conclusions from this. But I think we can say that it's at least competitive with some of these other systems. Surface roughness. This was the process that Wisconsin Precision used. They did a quick sanding and knocked down the build lines, and then vapor polished the part to smooth the surfaces. One of the advantages of the polycast material is that it can be vapor polished, which means if you expose it to vapors of a solvent, it will melt slightly the outside surface of that part and allow it to re-solidify and create a very smooth surface. You get very glassy surfaces this way. It smooths the surface and seals it, and Wisconsin Precision claimed that using that process gave them a surface finish that was adequate for their purposes. Now, they're general purpose investment casters. They're not aerospace or medical, which require better surfaces, but this yielded pretty good surfaces for that. Print speed. This can be very difficult to measure because it varies so much with different variables, like how many patterns you're building at a time, which way you orient it. I took a different approach in my study previously, and I did the same thing with the Ultimaker. I obtained some actual build data from multiple sources, people who are using that system to build investment casting patterns. And for each run, I calculated an apparent build speed. I divided the total volume of the patterns built by the build time, and that gave me cubic inches per hour for that run. Then I averaged the build speed, the apparent build speed over dozens of runs to get an estimate of the average print speed for that printer. And this is how they compared. Now the S5 is not a real standout here. It's much lower than the VX1000, which is the superstar here in terms of build speed, or the ProX 800, but it was 2.5 times the speed of the ProJet 3600. Printer cost. Here is a big difference. Some of these are very expensive machines, the VX1000, 800 and 6000. This is the printer itself, not any of the associated equipment. The S5 at 9100 is a small fraction of that. In fact, it's just over 1% of the most expensive system. But this isn't really a fair comparison because the print speed of all these different systems varies a lot. We can normalize that by calculating what I call the capacity cost. I take the printer cost and divide it by the build rate, and this is the cost of a 1 cubic inch per hour build capacity. If we look at that, now the Ultimaker is really the standout. It's much lower than these other technologies. In fact, this is covering up, here we go. It's 14% of the least expensive, 1/7 of the cost of the VX1000, which is the least expensive capacity cost before, and it's only 3% of the most expensive, the cast form, the laser sintering process. Looking at pattern cost, this is the other thing that's very important. Now, build cost or pattern cost has several components. There's the cost of the materials that go into it, the cost of depreciation on the machine that's building it, the cost of maintenance on the machine that's building it, and the labor that's used in building that part. Now, the labor is roughly equivalent from process to process, so I'm going to ignore that for the time being. And all the details on how I calculated this cost, well, I'll go into more detail in the longer version. But for right now, this is the total non-labor pattern cost per cubic inch. And here, the Ultimaker, again, comes out the cheapest. It's 1/3 of the cost of the VX1000, which is the least expensive one there. And it's only 6% of the most expensive, the ProJet 3600. Now, the last category, casting difficulty. This is how difficult it is to cast. And I won't go into the detail here, but ranking these terms of ease of casting, the easiest is the multi-jet modeling because we're printing and wax there. There's no change to the process at all. The PLA, the Ultimaker, has only a minor change. It's going to be very easy to incorporate into a running foundry. These other processes require much more difficult variations to their process and make it more difficult. So it's almost as easy as a multi-jet modeling. So to summarize our evaluation criteria, the build envelope, it's built big enough to be acceptable for many foundries. If the foundries making really large parts, it won't be adequate, but for the majority of foundries, they're going to find this be pretty useful for the parts they build. Accuracy, it's competitive with these other systems. Surface roughness, it's acceptable for most foundries, and with some handwork can be improved beyond what you can do with vapor polishing. Build speed, it's faster than printed wax, which is one of the more popular systems out there. System cost, it's the lowest printer price and the lowest capacity cost of the systems I looked at. Pattern cost, it's the lowest pattern cost. And casting difficulty, it's easier than all but the printed wax. So my conclusion is that the Ultimaker S5 printer running polycast is viable for printing investment casting patterns because compared to the leading systems out there, it has competitive printer performance, it has a lower purchase price, it has a lower capacity cost, lower pattern cost, and it's easier to cast than all but printed wax. Now, as the final thing, this is a chart that I used in my study before, and here I plotted the build cost versus the build speed. And obviously, we'd like to have a printer that has a high build speed and a low build cost. And there, the VX1000 in my previous study was clearly the winner there, followed by the Pro X800, followed by the S Pro 60, and finally the slowest and most expensive was the CPX 3600, the multi-jet modeling system. The S5 comes out here. It's got certainly the lowest cost, but it's pretty slow compared to some of those other systems. But it occurred to me, what if a foundry buys 8 of those printers? It's not going to affect their cost, but it's going to, now they're going to have 8 times the speed. So now we've got 8 here, and comparing that to the Pro X800, which is the most common system used to print investment casting patterns, build speed is greater than the Pro X800, but the purchase price is 1/5 that of the Pro X800. Pattern cost is less than 1/5 of the Pro X800. And another important consideration is reliability. If your Pro X800 goes down, you're out of business until you get it repaired. If one of your S5 goes down, you still got 87% of your capacity available that you can continue to run until you get that one printer repaired. So that completes it. I hope I finished in enough time. Thank you, and I'll entertain questions at the end of the hour, I guess.
Tom, thanks very much. Great information.